What are damping factors and what would we use them for? Well, they don't come up very often in pure math settings, but they have to do with sine and cosine. Remember, sinusoidal functions are the ones that are made from sine and cosine, and they model simple harmonic motion. So some examples of simple harmonic motion, if we take temperature over the course of day and night, it rises during the day and then falls during the night. The number of daylight hours over the course of the year. During the summer, it's at a peak, and in the winter, we have very little daylight hours. Altitude on a passenger on a Ferris wheel over time, or that should be of a passenger on a Ferris wheel over time. So the person rises, then they fall, hopefully not faster than the Ferris wheel, and that still follows this sinusoidal pattern. Predator-prey relationships. As the predator increases in population, the prey will decrease in population, and then as the prey decreases in population, the predator will increase in population, etc. So frequently, two sinusoidal graphs will have a phase shift between them because when the prey increases, the predator is decreasing. And movement of a mass on a spring. So we have the mass is moving like this, but if you actually graph that out, it's going sinusoidal. But if we really think about movement of a mass on a spring, that doesn't usually happen that way. We usually have a spring will slow to a stop. What's happening? Well, typically what you'll have is you'll have the spring will lose some energy. So the energy is lost, and the reason that it's lost is due to friction. So when it rebounds, it's not going all the way up to where it started. It's losing energy. It's getting closer and closer to equilibrium, and then eventually tapering off. My graph is imperfect because this looks like the period is decreasing. It's not supposed to decrease. It's just that the amplitude is getting smaller and smaller as we get closer and closer to infinity on the time axis. So what this looks like algebraically is it's a damping factor. A damping factor is a factor which changes the amplitude of a function over time. So we start with a high altitude, and then the altitude is getting smaller and smaller and smaller and smaller. So the envelope is the graph of a damping factor, and it's negative. So here's a graph of a damping factor, and the graph of its negative. And it bounds the function. So the function, the sine graph, will stay within the damping factor because the amplitude is going, when it equals the amplitude, it'll be at the top, or at the bottom, but the function can't get bigger than that damping factor. So if it loses energy, then the amplitude is going to get smaller, and we call these two functions the envelope of the sine function. So let's describe if we were going to graph this, going from -1 to 1. I chose my scale to make things easy on ourselves. Let's first consider what would it look like if we were just graphing cosine of pi x. Well, the period would be 2 pi over pi, so the period would be 2. So we're going to hit another maximum at 2, and then another maximum at 4, and then another maximum at 6. So minima will occur at 1, 3, 5, 7. But because of this 2 to the negative x, 2 to the negative x will look like this. It's going to decrease in amplitude. Now, if we're drawing the envelope, we should also draw the negative version of that. This is just a sketch. I'm not going to ask you to get a perfect graph of one of these. But if we were to graph this, we would take a maximum, and then it'd go down to a minimum, but that minimum wouldn't be all the way at -1. We'd put that minimum down here between -1 and 1, where 2 to the negative x would be. And then the next maximum would occur on the damping factor, and then it goes back to equilibrium, and then the amplitude is getting smaller and smaller and smaller and smaller. So what's happening? Goodness, I'm being a little messy. It's messing things up. There is what's happening. So we start with a large amplitude. We decrease the amplitude over time. So the way that you want to do this, in terms of how you would actually do this in terms of steps, graph the damping factor, which is your 2 to the negative x. Determine the period of your sinusoidal function, and then graph the sinusoidal function using the envelope. So, in other words, the colors that correspond to what we just did, first you're going to graph the green. You're going to graph the green 2 to the negative x and its reflection over the x-axis. Second, you'll determine the period, which is what we did up here in red. And lastly, we'll graph the curve fitting between the envelope. Thanks.